What's up, everyone? This is LeetCode 236, lowest common ancestor of a binary tree. We've done this problem similarly in 235, which is lowest common ancestor of a binary search tree. So really the only difference between these two problems is the problem we did before on the grind 75 list, it was a binary search tree, right? So the tree is actually ordered a specific way, whereas in this problem is a little bit harder because it's unordered. That's really the only difference between these two problems, okay? So our approach is going to have to change a little bit. So we just have to find the lowest common ancestor of two given nodes that we're given, which are P and Q, right? And the lowest common ancestor is defined between two nodes, P and Q, as the lowest node in T that has both P and Q as descendants, and we allow a node to be a descendant of itself, much like LeetCode 235, right? So if you haven't done LeetCode 235, like seriously, I recommend doing that one first. It's basically the exact same as this one. It's just a tiny bit easier because of how the tree is ordered. It's really good practice. Okay, so we're gonna basically have to solve this problem using recursion. Whereas like in LeetCode 235, where the tree is sorted, we know where we can go, left or right, right? If P and Q are both greater than the current node we're on, we just go right in the subtree because we know that all the values to the right in the right subtree are going to be greater than whatever the value we're on right now in a particular node. Meaning, let me just show you, obviously, rather than speaking, right? So if P and Q are like, I don't know, 10 and 30, right? And imagine we had a bunch more nodes here. We know that 10 and 30 are going to be bigger than this 6, so we can just go to the right. We don't have to consider anything here. Here, that's not the case, right? Because everything's unordered. And so that's kind of the tricky part. And so the way we're going to solve this is basically just use recursion, and we're basically going to handle the left subtree, then handle the right subtree. And, you know, did we find what we found? Did we find stuff in the left subtree or the right subtree or both? And kind of like that. I think we kind of did like a similar problem where it was like, I think diameter of a binary tree or something, I think the problem is called, where we basically have to go down and see if we find stuff. I guess this is bottom up kinda, but not really, because we are going down the tree when on the left subtree or the right subtree when we recurse. But if we find something, we're done, right? We go back up. So we don't go all the way down and then go up. So it's a little bit different. But anyways, that's my point. Like, it's just like a recursion tree problem. We've done these before. Assuming you've been following me on the grind 75, right? So what we're going to do basically is we're going to start at the root node, obviously, right? That's what we're given. And we have P and Q. Okay, so what do? Well, keep in mind, P and Q are guaranteed to be in the tree, right? It says right here in the constraints, P and Q will exist in the tree. So we won't have a case where P and Q won't exist. So this makes the problem a lot easier also. All the values are unique, right? So that's why you should read the constraints, by the way. It'll make the problem easier. But so we start at the root node, right? And what we're going to do is we're going to go to the left, right? First, on the left subtree. And we're going to see, do we find P and Q, right? And like when we're at this 3, we go left first, right? Okay, we found 5, which is actually one of the nodes. So we go back up and we say, okay, we found something, right? We found something. Now we're going to go to the right and we have to find 1. Oh, we found a 1. We found something. So we go back up. So there's something on the left subtree and the right subtree. So guess what? The LCA is 3, right? Because we have P over here and Q over here. So the LCA is actually 3. Very similar to LeetCode 235 if you've done that. Okay, pretty simple. But obviously that's a really simplified problem. Here we have P is 5, Q is 4, right? We're going to start at the root node. Okay, let's start with the left subtree. And we always go left and then right. And, you know, we don't like check any conditions necessarily before we go left or right, because again, this tree is unordered, right? So we're going to go left. Okay, we'll start this root node. Okay, is P and Q equal to 5, which is this node? Yes. So we basically return up and we say, okay, we found something on the left side. Now we go to the right. Do we find 5 and 4 here? No. Okay. Now let's keep recursing. We go left. Do we find something? No. We go left and right. No, because they're empty, right? Off the 0. Then we go back up and we go to this 8. And then we go, okay, is P and Q equal to 8? No. Left and right? No, nothing, right? So we go all the way back up and we go back to this 3. And on the right subtree, we basically go like, hey, we didn't find anything. So what do we do in that case, right? Well, if we didn't find anything in a particular tree, it means that P and Q must exist in the other side that we did find. Or that P and Q both exist on the other side. Because, I mean, think about it. When we're at this 3 and we go left, we hit a 5, right, which is P, and we go back up. Technically, Q could be here. I mean, we're returning, right, back up. So Q could be somewhere even lower in the tree, but we ultimately don't care because if Q is below this 5, it doesn't really matter because 5 is the LCA, right? That makes sense, right? Like 5 is obviously going to be above whatever. If 5 is P, if Q is below, P is going to be above Q in the tree, so P is going to be the LCA. So we don't really care if 4 is here or not. I mean, we do care, but like we don't have to like explicitly check for it. So when we go here, when we return up to this 3, okay, we have nothing on the left. Or we have something on the left because we returned back up, but on the right we found nothing. So that means that Q, which we didn't find here, it has to be somewhere over here because again, they're both guaranteed to be in the tree, right? So that means that this is the LCA, right? And so we return this as the LCA, which is oh sorry, I'm looking at example 1. This is what I meant, right? Because technically here the Q is 1, it does exist. I was looking at the wrong example, but this is the one we were just talking about. If Q is 4, right, and we go to the right, there's no 4 here, right? So we found P, which is 5. When we start at this 3, we go left, we found this 5, right? So we found P, but we didn't find Q when we go to the right here. And again, why would we not check Q? Because after we found P or Q, we return. So we don't keep going, right? So that's why we didn't. Technically, Q does exist here. It's just that we're not going to check for it. Okay. So we're at this 3 and we check the right subtree. We found nothing. So what does that mean? It means that 5 has to be the LCA, right? So that's kind of how we're going to handle this problem. I know it may be a little bit complicated the first time around, but I think if you do LeetCode 235, this one actually isn't that difficult to understand. I think if you're trying to do this problem without doing 235 might be slightly complicated, but it's fine. Okay, so first of all, we're going to do this recursively, right? So we need a base case basically where if there is nothing, we return nothing, right? Like when we're at this 0 and we go left or right, the child nodes, if there's no node, then we don't have to return anything. Okay, now if there is a node, we have to check if it's equal to P or Q, right? In that case, we return the root, right? Like if we're at this 3 and we go left, if 5 is equal to P or Q, we have to return whatever this node is. Okay, and again, we're doing this recursively, that's why I'm saying root. But root is actually going to change because root will change depending on what recursive call stack we're on. Which we'll do right here, which we're going to say search for the LCA in the left and right subtrees. Okay, so we're going to say left is equal to self dot list comment ancestor root dot left. We're going to say P. We'll just copy this because we're going to do the same thing, except we're going to do it for the right side. So we're going to say right, lowest common self dot lowest common ancestor root dot right P and Q. Okay. Now, if both the left and the right are non-null, this node we are on is the LCA. So we're going to say if left and right, return root. And then otherwise we'll say otherwise return either the left or right result. We're going to say return left if left, also right. So that's the code really. Okay, and I'll explain it in an image just so I can draw it really quickly. But really up here, what we're doing is like basically what we would do for example 1, right? So in example 1, like we go left. Okay, we found this 5 here, which is P, right? So we return back up, but we need to go in the right subtree, right? So we go to this 1. Well, 1 is equal to Q, so we return up again. So when we're at this 3, the left and the right subtrees both return something. That means that this 3 is the LCA, which is what we're returning, right? So yeah, that's basically like this would basically is what would give us our answer for example 1. For example 2 though, it'd be a little bit different, right? Because we're at this 3, we go left. Okay, this 5 is equal to P, so we go back up and we return this value. When we go to the right, we check everything, right? And we don't find P or Q. So technically, when we're here, left returns something, but right has nothing, right? It's a null, ultimately, because we never found anything. So in that case, we have to return left, which is this 5, right? Because that's we returned up from it. So this is actually the LCA, right? So yeah, I don't think I need to draw this. I think you should be able to understand, but I'll still draw it, right? So if P is 5, right, we're going to start here, and we're going to go, okay, let's go here. Okay, is this equal to P or Q? Yes, it is, right? So our left is going to be equal to this. Okay, now we return back up, obviously, and we go to the right. Okay, is this 1 here equal to P or Q? Yes, it is equal to Q, actually. So this is going to be equal to our right. So when we're back up, so we go back up again, and when we're up here, we're gonna say, hey, left has something, and so does right. That means this has to be the LCA, right? And that's what example 1 is. Sorry, that's why example 1 is the LCA. I have YouTube open, my bad. But yeah, this should be the LCA 3, right, for example 1. Example 2, the LCA should be 5, and I'll show you why, right? So we go left, right? Again, we start at the root node. We go left. Okay, is this 5 equal to P or Q? Yes, it is. It's equal to P, which is 5. This is going to be left. We're going to go back up, right? And we're going to go right. And again, when we go right, when we go to the right and we check recursively, we never find anything anywhere, right? We go back up, go up here, we go like this, then we go here, and we never find P or Q anywhere in this right subtree. We never found P or Q. So when we go all the way back up, right is basically just null, right? So in that case, return left if there is a left, otherwise return right. So there is no right, so but there is a left, so we return the left, which is 5, and that should be our LCA. Okay. And I'll just submit this really quick. Again, I don't think this problem is too hard. I just want to over-explain it just because we're using recursion. It can be a little bit confusing. But make sure you do LeetCode 235. Like, I promise you, if you haven't done it, it will make this problem easier to understand. Please do it. But anyways, I hope this helped, and I'll see you in the next one. Peace out.